Welcome to Mechanical Drawing and Design N6. Today's presentation is going to be on clutches. This is a module that you might have seen already in Mechano N6. If you did not struggle with it, then you will find this presentation to be easy to understand. Let's begin. First, we will look at plate clutches. And this is a simplified drawing of a plate clutch. And I will introduce to you some of the features on the clutch that you need to understand. And it's important for you to be able to visualize it, because then that makes it easy for you to solve questions that you may get in your exam. First, the outside diameter, we will refer to it with capital D. And that is that distance that you see. It's the outside diameter of the clutch. And then you also have the inside diameter, which we are going to refer to with small d. And then you have something that is referred to as the mean circle. And if you measure the radius of that circle, it is referred to as the mean radius, and we use the letters RF, okay? R with the subscript F to refer to the mean radius. It's very important to remember this. And so, generally, you will have an axial force that is acting on the plate clutch, and you will also have a tangential force that is acting on it, okay? And so this axial force is what will cause the clutch to get engaged. And the tangential force here is what allows it to rotate, okay, and to create torque. Because as you can see, the direction of the tangential force will cause this plate clutch to actually rotate like this, okay? And so it's because of the tangential force that you have torque, and you can find this tangential force using an equation that relates it to the axial force. And the axial force is the force that is acting in this direction. And for the plate clutch, the axial force is the force that actually causes it to get engaged. Okay, very important. And so we're gonna look at some of the important equations that are associated with plate clutches. The first one is that of the area. As you can see, you have an opening in the middle here. You have a hole here. So therefore, the area will be equal to pi by 4, the external diameter squared minus the internal diameter squared. Okay, that is very easy to see. And also the average pressure, okay, is given by dividing the axial force by the area. Okay, this P gives you the average pressure on the clutch. But you also have the mean pressure, okay, the minimum pressure, sorry. And this minimum pressure is given by this equation here. And generally the minimum pressure will occur on the outer radius of the clutch, okay? That is where you will have the minimum pressure. And you also have an equation for the maximum pressure on the surface of the clutch, and that one will generally occur on the inner radius, okay, here. Very important, and the equation for it is that. At first glance, you will see that you may think that these two equations are exactly the same, but they are not. The difference is that in the denominator, for the minimum pressure, you have the outer radius, whereas in the denominator for the maximum pressure, you have the inner radius, okay? Very important. And after the pressures, you also have the tangential force. As I said to you earlier, we can relate it to the axial force using this equation, okay? The tangential force is equal to the coefficient of friction multiplied by the axial force. And once you know the tangential force, you can find the torque, okay? I said to you that it is this tangential force that actually causes the clutch to rotate, okay? So it creates torque. And so the torque will be equal to the tangential force multiplied by the mean radius, okay? The mean radius is RF, and then multiplied by N. Now this N here is the number of effective sides that you have on a clutch. Okay, so generally both sides of the clutch will be effective. What that means is that this side is effective and the side there behind is also effective. When both sides of the clutch are effective, then N will be equal to 2, okay? That is when you're dealing with a single plate clutch. They will tell you maybe both sides are effective, therefore you will take the value of N to be equal to 2. When you're dealing with multiple plates clutches, then at that moment, N becomes the number of contact pairs, or if you want also the number of discs that you have, okay? So if you're dealing with a situation where you have multiple plates clutch, they give you a multiple plates clutch in a problem and you want to use the torque equation, the value for N that you will use will be the number of contact pairs that you have in that system, okay? Or the number of discs, okay? Because usually one disc will have two contact sides, okay? So one pair, one disc is equal to one pair, okay, of contact sides, okay? So just bear that in mind. If you're dealing with a single plate clutch, N is the number of effective sides on the clutch. Sometimes you have a clutch that only has one side that is effective, then N will be equal to 1, okay? But sometimes, and which is usually the case with single plate clutches, both sides will be effective, so N will be equal to 2. But if you're dealing with a clutch that has got multiple plates, okay, a multi-plates clutch, okay, if you're dealing with a situation like that, then N in the equation for torque is equal to the number of contact pairs or the number of discs, okay, because usually one disc will have a pair of contact surfaces, okay, so the number of discs is equal to the number of contact pairs. I hope I am making myself clear. So now let us look at the mean radius here, RF. So what is RF equal to? RF will be equal to this if you are dealing with uniform wear theory, okay? And RF is going to be equal to this if you're dealing with uniform pressure theory. So usually in your question, they will tell you whether you should assume that you're dealing with uniform wear or uniform pressure. Basically, when they say uniform wear, what is meant is that the clutch is wearing off uniformly, okay? So we assume that. If it's uniform pressure, then we assume that the pressure is uniform, okay? So that is what, those are the two theories that you will have to identify, okay? When you have a question, you will have to identify which of these two theories is in place so that you know which equation you will use to find RF, which is the mean radius, okay? So if it is uniform wear, you use that equation to calculate RF. If you're dealing with a situation of uniform pressure theory, then you will use this equation to find RF. Usually in the question, they will tell you which it is. And so once we know the torque, it is also possible to find the power. So the power is this equation that you've seen many times before. It's equal to 2 pi nt divided by 60. And of course, you divide by 60 when n is given in RPM. If you are given n in revolutions per second, you don't need to divide by 60 in this equation. But generally, they will give you n in RPM. Now, back again to uniform wear and uniform pressure, okay? When do you use uniform wear or when do you use uniform pressure if it is not stated clearly in the question, okay? So when to use uniform wear theory and when to use uniform pressure theory if it is not stated clearly in the question, because sometimes you may come across a question where they will not state clearly to you whether you should use uniform pressure or uniform wear theory. So what are you going to do? Okay, I did say that generally they will tell you which to use, but if they don't, then what do you do? Okay, so what you will do is this. If you are dealing with a clutch that is new, okay, you can assume uniform pressure. Okay, so therefore to calculate RF, you will use this equation. But if you're dealing with a clutch that has been used for some time, then you can assume uniform wear. Okay, and therefore you will use this equation to find RF. Of course, if a clutch is new, it hasn't worn off yet. Okay, it hasn't gone through so much time of rubbing against things so that it will wear off. Okay, so it is still new, so you cannot use uniform wear for a new clutch. And sometimes you can get a question also where they ask you to design a clutch, and when you are designing something, you can assume it that you're making a new design. Okay, so it hasn't worn off yet, and therefore you will use uniform pressure theory when you're dealing with a design or a new clutch. But if you're dealing with a clutch that has been used for some time, then you can say, okay, it has had the time to begin to wear off. And so for that reason, you will assume uniform wear theory. But you only do that if it is not clearly stated in the question which theory to assume. But generally, they will tell you assume uniform wear theory or assume uniform pressure theory. It's only when it is not stated that you can use this little piece of information that I just gave you. If the clutch is new, assume uniform pressure. If it has been used for some time already, you can assume uniform wear. Okay, very important. After the plate clutch, we will look at the cone clutch. Okay, and this is what it looks like in 2D. Okay, but in 3D, a simplified picture of a cone clutch is this, okay? It's also referred to as a conical clutch. It's the same thing, okay? So, and the reason is obvious. If you look at this looks like a truncated cone, okay? This is a cone that has been cut, okay? So you can see, that's why it's called a cone clutch or a conical clutch, okay? So this is what it will look like, okay? A simplified view of what it looks like, but in 2D it will look something like that. Okay, you can see also what we refer to as the big R, okay, the big radius, and the small radius, small r. You can see where we measure those. Okay, and so therefore that dimension here, which will be from here to here, what you see here is the big diameter. Okay, so we use capital D. And the one from here to here, which will be that length there, is the small diameter, okay? Very important to see. And also we have something that is referred to as the width, or also the face width of the cone, and that is that length there, okay? So if you measure the length from here to there, that is small w, and this is the width or the face width of the cone. Very important. And you also have another important geometrical feature of the cone, and that is that angle there, okay? This is what is called the semi-cone angle, okay? Very, very important, okay? This is basically half of the included angle of the cone. The included angle of the cone is the angle that you will get if you extended that line like that and this line like this, okay, where they will meet. If you measure that angle, that is the included angle of the cone. So alpha is half of that angle. That is why it is referred to as the semi-cone angle. Very, very important. And so the actual force will act in that direction, okay? And with cone clutches, you also have another force which is referred to as the normal force. And that one acts perpendicular to that side or that face of the cone, okay? And you also have the tangential force, which is responsible for the torque. And in this case, the tangential force will be into the page, okay? If we assume that this cone was rotating like that, okay? It's rotating like this. I hope you can see, okay? Basically, when I say it is rotating like this, I don't mean that the cone is doing this, okay? I mean that it's rotating about an axis that goes through the center of these two circles. So if you draw a line here from this point to that point there, and you have an axis like that, and then you have the cone revolving around that line, okay? So that is what I mean. So it's doing this, okay? It's rotating like this. I hope you can make sense of what I'm trying to explain, okay? So if we assume that this cone is rotating like this, the tangential force will be into the page because it will be going like that, in that direction, to try and rotate it like this, okay? So that's how the cone is rotating. So when we look at it in 2D, the tangential force is acting somewhere here, but it's into the page so that this thing will be revolving, okay? About the axis that passes through the center of the cone. Okay, so Ft is a force. That's why I just put the dot here, because this tangential force is a force that is into the page, okay, causing this cone to rotate like this. Okay, I hope you can make sense of what I'm trying to explain. Good. And so now let us look at some of the equations that are important with cone clutches. The first one is that of the area, okay? The area is equal to pi multiplied by the outer